So this is essentially part 2 of our theory for this chapter 25 stuff. And here we're going to start talking about the energy stored in a capacitor. So we know that to move a positive charge from the negative terminal of a battery all the way up to the positive or the upper plate of the capacitor, it takes work to do. And we know that the work it takes is equal to delta V times dq, where little dq is like, okay, we take a tiny little chunk of charge here and we move it up through this electric potential difference and all the way here. Now we know that the electric potential difference is equal to Q divided by C. So normally you see it as delta V is equal to capital Q divided by C, but when we're talking about an instantaneous moment in time, we tend to use lower cases. Because the idea here is that delta V, well, we're talking about the electric potential difference between the plates, and that changes. It starts off as being nothing, when there's no charge here, no charge here, and the more charge we place on this upper plate, the larger the electric potential grows. So then, if we say, okay, well, then this is what dW is, a little bit of work it takes to move this charge all the way down here, is Q divided by C times dQ. We want to know, well, how much work does it take to bring all of the charges onto this upper plate? Well, we take the integral going from 0 to Q, where Q is the total charge at the end, like how much charge we have when delta V here is equal to delta V battery. We take this integral and then we get Q squared, so capital Q squared divided by 2C. So this is the work done in charging the capacitor. Now we can also talk about this in terms of electric potential energy stored in the capacitor. And we say that, okay, well, this can also be that. So this is how much electric potential energy is stored in the capacitor. And that's what's written here. Now all that's done in the next two equations is we use this equation here where delta V is equal to Q divided by C, and we just plugged it in a few times to get a couple of different expressions, but it's all the same thing. So lastly, we can talk about energy stored in an electric field. All we're doing is taking the same equation and plugging in what we know in terms of E, right? So we know that delta V is equal to E times D for a uniform electric field situation. And we also know that C is equal to epsilon naught A divided by D for the parallel plate system, which is what we have. Plug all that in and we get this expression here. All that we do to get this final equation is say, well, okay, this is energy stored per volume. Volume, area times distance between, right? This is the volume of a space between the two plates. And then that is going to be equal to 1/2 epsilon naught E squared. And this is also known as the energy density for a uniform electric field. So next, we're going to talk about dielectrics, because I think this part is a little bit more important than the whole energy density stuff. The idea here is that we can increase the capacitance of a capacitor by placing an insulator in between the plates. So that's what we have here. We have our negative plate, positive plate, they have equal and opposite charge, and then we have an insulator. Now the idea is that an insulator, right, it has like, let's say, atoms of like positive core and little negative electrons floating around. And the negative electrons, they don't really want to move that far away from the atomic core. They like to stick around, but they can be polarized. And that's what we see here. Or when an insulator is placed inside of an electric field, so here the field is going this way, well, our atoms are going to kind of react a little bit and they're going to become polarized. Where here, the electrons are going to try to move as close as they possibly can to the positive side. And the positives, so the protons, are going to try to move as close as they possibly can to the negative. Right, so the idea is we have an electric field coming in, and we know that here, let's say the electric field's going this way. Well, the positive charges are on this side, the negative charges are on this side. So the positives are going to go a little bit closer to the negative, negative a little bit closer to the positive. And that's fine, that's what happens. But if we were to draw our electric field lines, we see here that they are inducing this electric field going to the right, which is in the opposite direction of our normal or original electric field that we call epsilon naught. So that's what's happening there. And we can say that, well, the original electric field, because we have parallel plate system, is sigma naught divided by epsilon naught, where this is just like the original charge density. And then our electric field that was induced, we call it sigma induced divided by epsilon naught. So our new electric field, it's just, well, the original one plus the one induced. But the thing is, the one that was induced is in the opposite direction. So that means that our new electric field is going to be less strong than our original one. We can then define this term that we call the dielectric field constant, here K, to be the original electric field divided by the new one. So because the new one is always smaller than the old one, K is necessarily larger than 1. We can talk about this in terms of electric potential, which we know is E times D. And we know here that E, right, this is the new electric field. Put this onto this side is going to be epsilon naught divided by K. Like all I did here was I said, okay, E is equal to epsilon naught divided by K. Plug that in here. But we also know that epsilon naught times D, that's just what the original electric potential was. So we see here, this is the new electric potential. This is the old electric potential. Again, because K is always larger than 1, the new electric potential is always less than the old or the original electric potential. So lastly, for the capacitance, we know that C is equal to Q divided by delta VC. We want to figure out, well, what's the new capacitance? Well, we know that delta VC from here, the new electric potential is this. And we also know that, well, we're shoving the same amount of charge onto our plates, right? Like that up here, that didn't change. We put a certain amount of charge here. So that's the same as it was before. Now we rearrange things and we get this equation where the new capacitance, once we've inserted this dielectric or insulator material, is K Q naught over delta VC naught, so the original electric potential. We know that Q naught divided by delta VC naught, this is the original capacitance, right? So then we see that the new capacitance is equal to K times the old capacitance or the original capacitance. And because K is larger than 1, the capacitance necessarily increases when we add a dielectric. So what does this physically mean? Well, when we had no dielectric, here let's say there's the battery, we started shoving positive charge onto this upper plate. The more charge we added to plate number 1, the stronger the electric field became between 1 and 2. That means the charge from 2 was getting repelled away, leaving the plate negative. So this is positive and this is negative. And that's what we saw originally. So that's pretty normal. But with a dielectric, well, the same thing starts to happen. So we start shoving positive charge here. This becomes more positive. This will become more negative as the positive charge leaves here. But the polarization of the atoms, so these atoms here in the dielectric material also get polarized. This leads to them creating an electric field pointing in the opposite direction. Because this new electric field is not as strong as it is before, our capacity to hold charge increases. So because this electric field decreases, there's less of a repulsive force. So that means we can keep shoving on more and more charge onto this parallel plate system. Now, this is only true up until a point. What I mean by that is, like, let's say we had a very huge electric potential here, or electric potential difference in the battery. So that means, like, there's a huge voltage. At some point, it's going to be so strong that it's going to essentially break our material. So instead of having this nice, like, here, this is positive and this is negative and it's polarized, if we send an electric potential so strong, this material will be such that, like, that electron's just going to fly away anyways. So our insulator starts acting like a conductor. And if it starts acting like a conductor, instead of having these little polarized things going on, it's just going to break fully, and the electric field is just going to get super, super strong.